Welcome and hello. This is a video tutorial on HEC HMS, and in this lesson I'm going to be discussing sediment transport, specifically for reservoirs, sources, and diversions, those three hydrologic elements. All right, what I have on the screen here is a hydrologic network that I've sketched out. I've got a sub-basin with a reach down to a reservoir, and then over here is a source element with a reach down to a diversion, and that diverts water to the reservoir and then the downstream direction to this junction. So this is a few features I sketched in for the purpose of describing the sediment transport. In order to enable sedimentation analysis, sediment transport, erosion, and deposition concepts within our HMS model, first what we need to do is click on the basin model here in the Watershed Explorer, and then over in the components editor where it says sediment, change that no to a yes. And once we've done that, then we'll have a sediment tab right here, which I cover the details about this in lesson 72. And then also all the individual hydrologic elements, such as our reservoir that I click on, now has a sediment method specified down here. At least that's true for a number of the elements. So we have sediment method, as well as if you click on the options tab, we would also have observed sediment for a time series data set, which can be used to compare observed data with the actual model results. So in this lesson, I'm going to discuss reservoir, the different sediment methods, as well as touch on diversion and sources. Okay, let's go ahead and get started with reservoir here. So I'll click on reservoir, and then I'll click on the main reservoir tab here. Reservoirs naturally accumulate sediment. Sediment flows into the reservoir pool, and then it settles out without actually being removed. Over time, this would cause a small change to the reservoir capacity because the storage capacity would change with that increased sedimentation as years pass by. So HMS allows us to model that situation here. So here we have sediment method, and then there's 5 different options. So I'm going to select a different option and then describe the parameters. The first option is zero sediment trap. I'm going to describe them in a specific order from a little bit easier to understand to more complex. And I think one of the simplest is zero sediment trap. I should probably also mention that trap efficiency is the mass of sediment retained in the reservoir pool divided by the total mass of sediment that enters the reservoir pool. So if all the sediment passed through the reservoir pool and none of it was trapped, that would be a 0% trap efficiency. And then just the opposite, if all of it was trapped in the reservoir pool, that would represent a 100% trap efficiency. So with that in mind, it would probably make it easier to understand what this first option is. Zero sediment trap basically means none of the sediment that enters the reservoir pool stays there. It all continues to flow through to the outlet. This is more realistic for smaller reservoir pools and during larger flows for event simulations, not for continuous simulation runs. It's almost like the reservoir doesn't even exist, or at least it doesn't exist as far as sediment trapping goes. For this particular sediment method, there's no parameters. That's why you're not seeing a separate sediment tab up here in the components editor. All right, so the next sediment method is going to be complete sediment trap right here. This is sort of the opposite of zero trap. This is 100% trap. All of the sediment that enters the reservoir pool stays there. This is more realistic for larger reservoirs that have a large residence time that's long enough for even silts and clays to settle. As with the previous sediment method, the zero sediment trap, this complete sediment trap requires no parameters, and hence we don't have a sediment tab up here in the components editor. Okay, the next sediment method is going to be the specified sediment. So now we have a non-zero and non-100% option where a certain percentage of the sediment will be trapped in the reservoir pool, and then 1 minus that percentage will pass through the reservoir pool, through the discharge. I'm going to click on this sediment tab here that now appears in the components editor, and we're expected to provide a sediment gauge, which is a time series data set, and a gradation curve. So what these data sets represent is the sediment that leaves the reservoir. The gauge data is going to be the time series data set. The gradation curve here is a paired data set representing the gradation curve, the particle size distribution of sediment that leaves the reservoir outlet. All right, so to get these types of data sets, I'm going to go up to components. Let's see, sediment gauge would be a time series data set. So I'm just going to go ahead and create these for fun. Let's select the type being right here, sediment load gauges, and then click new. And then I'll just call this sediment reservoir 1. Okay, and create. We'll close that. And then if I scroll down to the time series data sets, sediment reservoir 1, I can define that by specifying a time window and then putting in the data right here. This is sediment load in tons for every 15 minutes, but I can change the date range and the time interval, of course, which is the case for every time series data set. But just so you know that it's in units of mass. And then there's a graph, and I can change the time window as well as the units and time interval here. All right, with that set, let's go ahead and create our paired data set. This is going to be for the grain size distribution. For the data type, I'm going to select diameter percentage functions and then click new. We'll call this grain size distribution reservoir 1. Oops. And then click create. Okay. Now for this data set, I can also define the data with a manual entry or a DSS record. If it's manual entry, it would be like the size of the grain size, and then the percent finer, so your grain size distribution. All right, let's go back to that reservoir now, and then select the sediment tab, and now we should be able to select our data sets. Okay, so that's how that works. Okay, let's go back to the reservoir tab here in the components editor. The next settlement method is going to be Chen settlement trap. So when I select Chen and I click on the sediment tab, we have a few different parameters here. This method mentions the comparison between settling velocity and the critical settling velocity for each particle size in the reservoir pool. Settling velocity is based on science. It's based on the particle size primarily, plus a few other factors to a lesser extent. The critical settling velocity is the discharge rate from the reservoir divided by the surface area of the reservoir. The surface area of the reservoir is a calculation that's required for this use, and that means that the reservoir geometry must also be defined. So our parameters here are the method. It can either be an average temperature or a time series data of temperature. If I click average, you can just go ahead and type the average water temperature in the reservoir. But if that changes, then you can specify the time series of the water temperature. So to do that, we'll go up to Components, Time Series Data Manager. Now we want to select temperature gauges in the new. Okay, so I'll just call this water temp reservoir 1. And then we can define that water temperature reservoir 1 the same way as any time series data set by specifying the units, the time interval, and yeah, we wouldn't need reference height or anything. This is sometimes used for air temperature, but we can go back to our reservoir now, click on the sediment tab, and then we should be able to select that water temperature time series data set because the settling speed is a function of the water temperature. The next parameter down is reservoir capacity method, and that's a yes or no. So if we want to take into account that the volume of the reservoir pool decreases as increased sediment accumulate on the bottom, we would click yes here. And then what we want to do for deposition shape is just specify the shape of the sediment. So V shape or elongated taper. I was actually looking at the 4.13 user's manual and was a little confused because they have a deposition shape for both clay, sand, silt, and gravel. So if you're using a later version of HMS than I am, you should expect to see 4 different deposition shape fields. You'll specify with using either of these 2 values. All right, now our last reservoir sediment method is coming up. It's going to be Brune sediment trap. So let's go back to the reservoir tab, click on Brune, and then sediment. This method computes the reservoir sediment trap efficiency based on the reservoir's total capacity and its annual flow. So I assume that there's going to be less trap efficiency with higher flows and vice versa. But what you're going to do is type in the annual average inflow volume right here. So I'm going to just type in some numbers that the user manual shows in its screenshot. The capacity elevation feet. This is the elevation of water surface in the reservoir at full capacity. And then constants A and B are set at 97 and 6.42. The range for constant A is going to be between 95 and 100. And then for constant B, that's going to be between 5.37 to 7.71. No additional information about these constants was provided in the user's manual, but I'm sure that information is out there. Lastly, we have this reservoir capacity method. If you want to account for loss of volume, go ahead and click yes, and then specify that deposition shape again. So that is it for the reservoir sediment methods. We talked about these 5 methods here and then their parameter values. There's 2 other types of hydrologic elements I want to cover, starting with source. So up here in the basin map, I'm going to click on source. The source element provides a way to introduce inflow to the channel network. Usually the inflow represents a portion of the upstream watershed that is not explicitly shown in the model. This is oftentimes to simulate boundary conditions to simplify or encapsulate a larger network that doesn't need to be modeled. Also, with the inflow comes sediment, and that's when we have our basin model set to monitoring sediment. So if I click on this source element here, we have a sediment method right here, which we'll talk about. And then again, in the options tab, we have observed sediment. So let's go back to the source tab in our components editor. And the 2 separate sediment methods are specified load and annual load. We'll start with annual load first. This method applies an average annual sediment load to the discharge hydrograph, which is suitable for continuous simulation of HMS. I'll click on the sediment tab here, and now I'm going to specify the tons per year of total load. So we'll just type in a huge number. This is the amount for all the grain sizes combined. So your silts, clays, sands, and gravels, and then all the subsizes within those larger groups. And then the units here is in tons per year. So just keep in mind that it's mass per time. All right, the next field down is the exponent. This is used to distribute the sediment load into a time series sedigraph. A smaller exponent value flattens the sedigraph compared to the hydrograph, and a larger value heightens the sedigraph compared to the hydrograph. And then lastly, right here, we have a gradation curve. So I could go ahead and set the gradation to what we already have it as, but it would probably make more sense to have a separate gradation for this source than for the reservoir. So what I'd do is I'd go up to Components Editor, create a new paired data set to represent the grain size distribution at this source 1 hydrologic element. All right, so I'm going to go back to the source tab here, and then for sediment method, I'm going to change it to specified load. Now we've already seen this with the reservoir to have a specified load where we could select the sediment gauge and the gradation curve. As you can see, I've already got that defined. I'm not going to do that for source, but you would do it the same way. You would create and define a time series data set for your sediment gauge, as well as your paired data set for the gradation curve associated with source 1. And then you'd come back to the components editor right here to make that assignment and save it. All right, the last hydrologic element I want to discuss is diversions. So if you click on the diversion element in your model, what I have in my model is the source flows to the diversion and then continues flowing down to junction 1 here. However, there is some diverted flow that goes to reservoir 1. This right here is the diversion, and then this right here is the main outlet. If I click on the diversion element here and then click on options, you can see I do have observed sediment once again. And then if we could click on the main diversion tab here in the components editor, my options for sediment are passage efficiency and specified load. Now we already talked about specified load twice in this lesson, so I'm not going to talk about it again, but just so you know, if I click on specified load, we have to specify that sediment gauge and gradation curve. All right, so now the option of passage efficiency. So if I click on passage efficiency, now I need to specify the percent of clay, silt, sand, and gravel of the original concentration entering the diversion that actually exits through that diversion passageway to my reservoir 1 in this situation. These percentages here refer to the percentages of concentration of each soil type that enters the diversion element. So for instance, if I had X parts per million of clay, let me just type in some numbers here, 98, 90, 28, and 2. So how about silt? If I had X parts per million of a concentration flowing from source 1 into this diversion element, And that means 90% of that X parts per million is the concentration that gets diverted out to reservoir one. As you can see, the larger particles have a lower percentage. So for instance, for sand, if I have a Y parts per million of concentration of sand from source one down to diversion one, then only 28% of that Y parts per million concentration of sand is in the diversion from diversion one to reservoir one. When the AGU 20 grain size classification is used, then the same percentage is used for all the subclasses of clay, silt, sand, and gravel. All right, well, I told you there were only three, but I do want to very briefly talk about junctions and sinks. So here is a junction. Junctions have no ability to store water, and hence they have no ability to store sediment as well. So any flow or any sediment that enters the junction will also exit the junction at the same time step. The total incoming sediment load equals the total outgoing sediment load of a junction, and that's what creates the sedigraph. And the last hydrologic element is the sink. I don't even have a sink element yet. Okay, now I do. In HMS, water or sediment leaves the model at the sink element. It doesn't continue on and leave the sink to another hydrologic element. The total sediment load that enters the sink is added to compute to the total sedigraph. All right, well, that was it for this lesson. We talked about reservoirs, sources, and diversions, and the different sediment methods and their parameter values here using HEC HMS.